Hi all, let's take a look together at the problems on your second practice test. I really think that there's a lot of fun problems on here. I'll try to make sure I take as much time as I can to explain how we are supposed to go about working each problem. You can see that the first problem has 4 parts to it, an A, B, C, and D. I'm wanting you to work with a quadratic equation and express it in standard form. And the way that we write it in standard form is through completing the square. And then after we get it in that standard form, we should be able to recognize what the vertex is. We can solve, set it equal to 0 to find the x-intercepts. The y-intercepts is easy. It's just f evaluated at 0. I already know the y-intercept is at 2. We'll sketch a graph and we'll determine the domain and range. Of course, the domain for any polynomial function is all real numbers. But let's go ahead and take a look at that first one. So here's the problem I gave. And I said, okay, please write this in standard form. So you say, well, that has to be a binomial quantity squared plus or minus some variable. How do I get that? Well, I can't get it from what I have because this is not a perfect square trinomial, because 2 is not a perfect square. So I just separated the 2 from the terms of x, and then I said, what term do I want there? And it is always half of b quantity squared. Well, I said half of 2 is 1. 1 squared is 1. So I need to put a plus 1 inside there. And you'll see I did it in red because that's just showing I went back in later and did that. So I want a plus 1 there, but I can't add 1 inside that trinomial unless I subtract 1 on the outside. Now, part A, to write this quadratic in standard form, you can say, well, this trinomial, it's the same thing as always x minus half of this number. It's x minus 1 quantity squared. If you multiplied x minus 1 times itself, you'll get that trinomial back. But now it's x minus 1 quantity squared plus 2 minus 1 for a total of plus 1. So now in this format, we know that this is just a parabola that's been shifted 1 unit to the right and 1 unit up. So you'll automatically see for when I graphed it here, I knew that the vertex was at 1, 1 just from this standard format. Now, some other things that we had to find, the x-intercepts. If I would have just went ahead and graphed this one out with the vertex, and I knew that the y-intercept was f of 0, which is 2, I would already know, hey, there are no x-intercepts because this is a positive parabola that points upward. It's not going to have any x-intercepts. I went ahead and showed that anyway. In general, the way that you solve for x-intercepts is you say, well, I'm going to set whatever my function is equal to 0. But when I try to do that here, I get the group x minus 1 squared is equal to negative 1. And then I can say, well, can I solve that out? No, because then when you try to take the square root of both sides, you'll get x minus 1 is equal to the positive or negative square root of negative 1, which is defined to be the imaginary number I. So automatically, since x is going to be answered in terms of the imaginary number I, you know it has no real numbers where it's crossing the x-axis. So I went ahead and found the complex solution here. X is equal to 1 plus or minus I, but then I just showed, well, that just means there's no x-intercepts. So we had our vertex from the standard form. We know there's no x-intercepts. As I've said a few times, the y-intercept is just the function evaluated at 0, which is going to give us the 2. And so then you could go ahead and connect your graph in there. The only points I just have to see is the vertex and the y-intercept here. If it had x-intercepts, you would show those on the graph as well. Now we know that the domain of all polynomials, and quadratics just a subsection of polynomials, they go forever to the left, forever to the right. Their domain is negative infinity to infinity. The range of every quadratic is going to be restricted. It always has a maximum or minimum y value. In this case, we have a lowest y value, a minimum y value. So I can say the range is going to consist of all y values between lowest y value is 1, goes up to infinity. 1 is included, so you need to say y equals bracket from 1 to infinity. Now, for the next two problems, I'm going to give you some functions of f of x that are already in factored form, which makes it very easy to find the x-intercepts, and I'll ask you to sketch out a graph of them. And what I'm most interested in this graph is the behavior at each x-intercepts and the end behavior of the graph. So now for number 2, I'm giving f of x is equal to x cubed times x plus 2 squared times x minus 5. So if I multiplied out the terms of x, I would have x to the third times x to the second times x to the first. That's 3 plus 2 plus 1. I'm going to have an x to the sixth. And I know it's going to be a positive x to the sixth because every single one of those terms of x are positive. So I can say, well, if I multiplied out the leading terms of x, I would get an x to the sixth. Yes, there's going to be other terms, but those other terms are irrelevant to the end behavior of this function. We know all positive even functions start high and end high, just like a positive x squared starts high and ends high. So I can say, okay, I know that. But now there could be a bunch of turning points and stuff in between. That's why I leave the gap. Now, in order to answer out what it looks like between the starting point and the ending point, I can say, well, it's going to have x-intercepts. If I set each of my factors equal to 0, this first factor equal to 0 just gives me x equals 0. Anytime a factor is to an odd power greater than 1, we know that the behavior at that x-intercept is it's going to slide through the x-axis at that x value. Now in my next one, x plus 2, if I set that equal to 0, I would get x is equal to negative 2. Well, what's the behavior at the x-intercept x equals negative 2? It came from a factor to an even power every single solitary time. If a factor is even, then the corresponding x-intercept will not cross. It only touches at that point. So we have the slides for odd powers greater than 1, touches for any even power. And then if it's just a factor to the first power, which is normally the case, then you can say, well, if this factor set is set equal to 0, you're going to get x equals 5. And what do I know at that value? It's just going to cross through at 5. And the difference here, if it's crossing through at 5, it's like a linear function at 5. If it's sliding through, you need to think of it as like a cubic function where it flattens out as it crosses. Okay, now I draw this out. I knew it started up and it ended up. Now, my very first x-intercept is at negative 2. I had to show that it touched there. So it came down, touched at negative 2, went back up. And then I can say, well, my next x-intercept. Now, if I know I have x-intercepts at negative 2 and 0, and I know it's going up here, it's probably going to hit a maximum right in between negative 2 and 0. So you'll see I went up to about x equals negative 1. Then I flattened off and said, okay, it's going to have to start coming back down because it has another x-intercept. And at this x-intercept, it slides through. So I had to show it's going to come down and flatten off through there. And it's going to slide through. This looks like a negative x cubed through this portion of the graph. So I can say, okay, it slides through at 0. My next x-intercept is not until 5, so it's going to come down, probably hit a minimum value somewhere around 2.5 to 3. Doesn't matter exactly where that x value is. We determined that in calculus. Right now we're just doing a sketch of the graph. It doesn't have to be precise. So it's coming down, it's going to hit a minimum somewhere between negative 2 and 3. Then it's going to have to come back up because it has another x-intercept at 5. What happens at this x-intercept? It just crosses straight through. So you say, oh, it's because it's degree 1, it just crosses in a linear pattern at that point. Absolutely. And so then you could say the end behavior is correct and the behavior at every x-intercept is correct. Gorgeous. The next one here, if we have f of x is equal to negative 2 times the group x plus 6 squared times the factor x minus 4 to the 5th times the factor x minus 8 to the 7th. The first thing you should always do is think about what that leading term is. So that negative 2 would multiply all of the highest power of x's, and you're going to have negative 2 times x to the second, understood third, because 2 plus 1 plus 5 is 8. plus 7 is 15. My leading coefficient or my leading term of this polynomial will be negative 2x to the 15th. Now, what am I supposed to know about every single negative odd function in existence? Every single one of them starts high and ends low. They could have a bunch of turning points in between, but I know that that is the end behavior. Now, with that in mind, I go in and I look at where my x-intercepts are. If you have a factor of x plus 6, then you're going to have an x-intercept when x plus 6 is 0 or an x equals negative 6. And I know that that factor came from a group that was being squared, so it's only going to touch at that x-intercept. My next one, x was a factor in its own. Well, if you set that equal to 0, clearly x is 0. And that's just a single power, so it's going to cross straight through at x equals 0. The factor x minus 4, if I set that equal to 0, you would get, well, x equals 4. And you know that that came from a factor to the 5th power. It's going to slide through at that point. Same thing with the last factor. If I set x minus 8 equal to 0, it tells you that there's an x-intercept at x equals positive 8. And the behavior at that x-intercept, since it came from an odd factor, is it's going to slide through at that x value. Okay, so now I go in and I start trying to graph my function. I know it starts high, so I started up here. And then I came down. I had to show it's going to touch the x-axis at negative 6. But because that came from a factor of even power, it looks just like y equals x squared there, and it's going to go back up. So the next x-intercept doesn't occur until 0. So I can say, well, it's going to go back up, and it's going to hit a maximum value right around negative 3. And then it's got to come back down because it has another x-intercept at 0. And now what happens at 0? Well, that x-intercept came from a factor degree 1, so it just crosses straight through at 0. It doesn't touch like it did when it was squared. It just crosses straight through. Now I look and I can say, well, my next x-intercept is at 4. So this is probably going to hit a minimum value right around x equals 2. Then it's going to start heading back upwards. Now, when it starts heading back upwards, I know it will cross at 4. But not only does it cross at 4, it doesn't look like it does at 0, because at 0, that came from a factor degree 1. This one, anytime the odd power is greater than 1, yes, it crosses, but it crosses in a sliding pattern. So I had to go up, show that it slides through at x equals 4. And my next x-intercept is not until 8, so it hits a maximum at about 4. Sorry, it has the next intercept at 4. Hits a maximum value right around 6. And then it starts coming back down. Now, I know it's going to cross at 8, and again, it crosses in a sliding pattern because of the odd power. My function is going to look something like this right here. Now, up next, we had the problem, I believe it looks like I did long division. Let me go to the, yeah, here we go. Yes, it says use long division to divide the polynomial 2x to the 4th plus 3x cubed minus 7x minus 10 by x squared minus 2x. Okay, so what I did for that problem, obviously the long division, I just wrote down the problem with the old long division sign. And you can say, all right, the way that you do this every single time is you take the leading term here and divide it into the leading term here. So I say, well, x squared will go into 2x to the 4th, 2x squared times. Now I multiply 2x squared times this entire polynomial. 2x squared times x squared is 2x to the 4th. 2x squared times a negative 2x, it's going to give me minus 4x to the 3rd. Now at that point, I can say, all right, I know I'm subtracting this group out. That's why the 2x to the 4ths cancel out. It's because I'm subtracting this group. I don't know how many times I see students do these problems wrong and they'll put negative x cubed as the next term here. That is not correct. We're subtracting this group out. That's why the 2x to the 4ths cancel. But then you'll have 3x cubed minus a negative 4x cubed. That's plus 4x cubed. I get a total of 7x cubed. Then I bring down my other two terms. Now, each time, if you're getting rid of the first term, you're doing your job. So now I say, well, what do I need to multiply x squared by to get 7x to the third? I can say, well, 7x. So I put a plus 7x up here. That positive 7x times x squared is my 7x cubed. 7x times a negative 2x minus 14x to the second. I subtract this out. Yet again, you can see the 7x cubes cancel, which is precisely what they were supposed to do. But I need to be careful. My second term is not a like term with the second term here. So I just bring it on down. I can say, well, that's minus a negative 14x squared, which is 14x squared. Then I'll bring down the two terms that had no like terms with them. Now I keep on doing this process as long as the power of x is not less than the power of x I'm dividing by. So I can say, oh, I can do it one more time. X squared will divide into 14x squared 14 times. 14 times x squared is 14x squared. 14 times negative 2 gave me a minus, 14 times a negative 2x gave me minus 28x. I subtract that out. The 14x squareds cancel. Negative 7x, this is going to be plus 28x, gives me 21x. I bring down the minus 10. And remember this 3 dots, if I haven't said it, that stands for therefore. It's mathematical notation for therefore. I did this long division problem. Therefore, I can say the original problem of this quotient is equal to the part that divided out evenly, 2x squared plus 7x plus 14. Then the remainder, the reason we call that a remainder is it's still being divided by this. So you say plus 21x minus 10 still divided by x squared minus 2x. Nice problem there. Now, the next problem asks us to do a problem with synthetic division. And instead of going back to the Word document, I'll just go ahead and point to it right here. This is the problem we were asked to synthetically divide. Now, it's a tricky problem, and I love that because something that I need you to keep in mind, whenever we skip terms of x with long division, you don't have to put them in there. So this skipped the x squared term. I didn't put a 0x squared. I just needed to be careful down here that I didn't try to combine the 7x with the 14x squared. So you don't have to put them in the long division. If there's any missing term in these problems, you have to put it in the synthetic division. And the thing about this one that's tricky is someone might say, hey, there's not a missing term of x. Well, I promise you, if you just try to use synthetic division with the coefficients 2, 1, 8, and negative 3, it's going to treat that as 2x cubed plus 1x squared plus 8x minus 3. So you have to stipulate that there is no constant in this problem. So you absolutely have to account for the 0 constant. Otherwise, these are not representing what they're supposed to represent. So we say, okay, that's constant, that's x squared, that's x cubed, that's x to the 4th. Nice. Now, remember your synthetic divisor is the 0 that you're dividing by. Another common mistake I'll see students do in problems like this is they'll say, well, why aren't you dividing by negative 2? That's the number there. It's not the 0. If x minus 2 is a factor, then x equals 2 is the 0. So you say, okay, you always divide by the 0 or the solution. So the solution to that factor would be 2. I synthetically divide with 2 into these terms. We always bring down the first number. Then you say 2 times 2 is 4. We add the next column. 1 plus 4 is 5. 2 times 5 is 10. 8 plus 10, 18. 2 times 18 is 36. Negative 3 plus 36 is 33. 2 times 33 is 66. And then the sum of the next column, still 66. Now, what this is telling us is that then that original problem is equal to, whenever you're trying to read your answer, you know that this is the coefficient of 1 less power of x than what you started with. So I know that this is 2x cubed plus 5x squared plus 18x plus 33. And then the remainder 66 is still divided by this. So I get my 2x cubed plus 5x squared plus 18x plus 33 plus 66 over x minus 2. Now, if let me see if I can clear that. It's a little blurry there. It's a little better. Now, for the next problem here, it was asking us to look at one of these where we find or use the rational zero theorem. So it said, use the rational zero theorem to list all possible rational zeros of f of x is equal to 5x to the fifth minus 3x to the fourth plus 2x cubed plus x squared minus x plus 8. What I need you to remember is that whenever you're trying to find the possible rational zeros, it's always just positive or negative factors of the constant divided by factors of the leading coefficient. That's always going to work. So for this problem, if I was trying to find the possible rational zeros, I would just say, well, it's positive, negative. The factors of the constant at the end, factors of 8 divided by the factors of the leading coefficient, 5. And so then it's just a matter of thinking in my head, what numbers go into 8? That's 1, 2, 4, and 8. What numbers go into 5? Nothing more than 1 and 5. Now, I do need to account for the fact that these factors could be positive or negative. So please notice you have to keep that plus minus sign in every step. Now, please don't just stop here. I actually need to see the potential or the possible rational zeros. So all you have to do is take each number in the numerator, divide it by each number in the denominator. So I have 1 over 1, 1 over 5, 2 over 1, 2 over 5, 4 over 1, 4 over 5, 8 over 1, and 8 over 5. Positive, negative of all of those values, that would be your final answer there. Pretty easy problem. Now, for one that may not be as easy, oh, nice, yes, I like it. Find all the zeros of f of x is equal to 3x to the fourth minus 5x cubed minus 16x squared plus 7x plus 15. All right, so if I'm finding that, the way that I would start this problem is I would use my calculator to help out. Now you're like, well, how's the calculator going to help out? Rather than going in and just using the possible rational zeros and then just trial and error figuring out which one works by synthetic division, I don't want to waste my time, particularly when I'm taking a test. So what I would strongly recommend is go ahead and find a zero that you know is. Now, you can already see I've shown -1 as a zero. Let's show where I got that from. All I did is I typed in my function, 3x raised to the fourth, and then I had minus 5x raised to the third, minus 16x to the second, plus 7x plus 15. Now, I was pretty sure that everything would be between -10 and 10 anyway, so I'm just going to go zoom 6. Is this going to be a great graph? No, and it doesn't need to be. All I need to see is where it's crossing the x-axis. And so, yeah, I can definitely see that. Now, I'm going to go in and say, well, it looks like it's crossing the x-axis 1, 2, 3, 4 times. In order to get a nice, easy x-intercept, I can say, well, when it's crossing the x-axis, it's crossing y equals 0. It's easier if you'll enter in a 0 in y2 now. Now I go back to my graph. I can say, well, I want to find one of those intersections. Second calc 5, you could just hit enter 3 times. Enter, enter, enter. And you'll see, hey, it went to the one I tried right there. Now, as soon as I can see, yes, there is an intersection at -1, 0. There is an x-intercept at x equals -1. Then show what happens to your function by dividing that -1 into it. So I take the 0, divide it into this synthetically, 3, -5, -16, 7, and 15. I didn't have to put any zeros because every single value is accounted for. I brought down the 3. -1 times 3 is -3. Sum of the next column is -8. -1 times -8 is 8. Sum of the next column is -8. -1 times -8 is 8. 7 plus 8 is 15. -1 times 15 is -15. And should I be surprised that I'm getting a 0 remainder? No, I knew it had to be. So this is just a confirming fact that, oh yeah, okay, I got the value that I wanted. Now, if I would have tried to get another one here on the calculator, notice if I go over here, second calc 5, and it looks like there's maybe one further to the left than -1, so I'll go enter, enter. When it says guess, I'll just scroll all the way over to the left, and that's going to guarantee that I get the one on the left. And I can see it's an irrational number, -1.468375. Not helpful. I want exact values. So I can just say, all right, I can't use that for synthetic division, so move on. Second calc 5, enter, enter. Now, I want to guess another intersection, so I'll guess this one. You know, like, wow, you're not doing well, John. Well, I knew it. That one wasn't going to give me a value, 1.135. So these two are irrational. Remember, irrational roots always occur in pairs, so I know that this one is not irrational. It's going to be a nice answer. Second calc 5, second calc intersect, enter, enter. On guess, arrow to where you want it at. We want it right here. It's going to be a nice value. Boom! Yes, it is a nice value. Okay, so now I knew, because irrational answers, just like complex answers, they never just occur in isolation. If I have one irrational decimal answer, I'm going to have another one. In this case, so I knew I had two, so the other two were going to be nice whole number x intercepts. So here's my other nice whole number x intercept. I show it synthetically divided into what I have remaining here. Please don't go back and divide it into the original. That would be wasting time. You divide it into the polynomial that you have remaining after the first division. And you can see when I did that, the 3 times 3 gave me 9. -8 plus 9 is 1. 3 times 1 is 3. -8 plus 3, -5. 3 times -5, -15. And yet again, we get a remainder of 0, which we knew we had to get. Now, I ask you to write this function in terms of its linear factors. So already, we know we have a solution at -1. We know we have a solution at 3. If you have a solution at -1, it means you have a factor, please be careful with that, of x plus 1. It's always the opposite sign inside the factor. And you can think of it, well, if x is equal to -1, if you move that -1 over with the x, it becomes x plus 1 equals 0. Same thing, if x is equal to 3, then x minus 3 is equal to 0. So your factors are x plus 1 and x minus 3. Now, the remaining factor I got from this right here, I knew I used synthetic division twice, so I would have reduced this down by 2 degrees. So this is a 3x squared plus 1x minus 5. Now, I already knew that is not going to factor because it has irrational solutions. So what I did here is I just went ahead and found those solutions. You could have used the quadratic formula. That probably would have been easier. But because I'm trying to get you to be a little more sophisticated with your solution procedures, I went ahead and used completing the square. If you would prefer to use quadratic formula, that's okay. Now, in using completing the square, I said, well, I'm going to put the x terms on one side. I'll move the 5 to the other. Now, you can't have a perfect square trinomial as long as that leading coefficient is 3, because that's not a perfect square. So I had to factor the 3 out of the terms of x. Now that I did that, I can say, well, that 1x became 1/3 x. Now, what number do I need there? Every single solitary time, it's half of b squared. So I said, well, half of 1/3 is 1/6. 1/6 squared is 1/36. That's the number I need here to add in. Now, please notice what I did on the right-hand side. I didn't just add 1/36. This 1/36 is inside of a group that's being multiplied by 3. So I'm really adding 1/36 times 3 to the left, so I add 1/36 times 3 to the right. Now on that left-hand side, this is going to become 3 times the group. The binomial squared that's equivalent to this trinomial is always the square root of the first term. You keep this sign, and then it's half of this number, or you could say the square root of this number. Same thing either way. So I'll get, oh, it's x plus 1/6 quantity squared. If I said x plus 1/6 times x plus 1/6, you would get that trinomial back. So now I can say, okay, I'm making progress. Now what about the right-hand side? Well, I knew that this was equal to 3 over 36, which is 1 over 12. So then I thought, well, 5 is 60 over 12. 60 over 12 plus 1 over 12 gave me 61 over 12. So then I can say, well, now I need to divide by 3 on both sides. If I divide by 3, that's the same thing as multiplying by 1/3 on this side, gave me 61 over 36. Then from this step to this step, I'm taking the square root of both sides. And we remember the side not containing the variable you're solving for is the positive or negative root. The root of 61 is irrational, so I just have to do that. But the root of 36 is 6. So I can say x plus 1/6 is the positive or negative root of 61 over 6. Now, if I solve for x, you'd say, well, I'd have to subtract that 1/6 on both sides, and I would say x is equal to negative 1/6 plus or minus the root of 61 over 6. But here's where I need you to remember the connection between a solution, or you might call it a zero, and a factor. The factor is what happens when both of these terms go back to this side, and it might actually be easier to look at the previous one. You can say, well, when those terms go over here, that 1/6 is always adding. This is the term that's going to change sign. When it's positive on the right, it's negative on the left. When it's negative on the right, it's going to be positive on the left. That's where these two factors here came from. X plus 1/6 minus the square root of 61 over 6, and the last factor, x plus 1/6 plus the square root of 61 over 6. Fully factored final fantastic form of the final answer. Gorgeous problem. Now, for number 8, let's see. Find a 4th degree polynomial given some criteria. And the criteria I give you here is that you have the imaginary root 2 plus I, and then the real roots at -3 and 3. So zeros of 2 plus I, -3 and 3. And then you're also known, or it is also known that f of 0 is 90. That's going to allow us to account for if there's some constant multiple stretching out our functions. It doesn't affect the x-intercepts, but it affects the y values of how far it's being stretched out. Okay, so now the first thing you're supposed to keep in mind here is you can say, just like he mentioned in number 7, where he said you can't just have one irrational solution, you have to have 2 because they occur in pairs. Same thing with complex solutions. I can't have the solution 2 plus I in isolation. It's impossible. So you say, there's another 0 at 2 minus I. Complex solutions always occur in complex conjugate pairs. So I wrote down the information, and then I said, well, since x is equal to the root, or sorry, since x is equal to the 0, 2 plus I, that means its complex conjugate is also a solution, x is equal to 2 minus I. Now, so f of x is equal to some constant c that doesn't impact the x-intercepts at all. It's just going to impact the possible y values. So some constant c times these are my 2 complex factors. This one, if you bring the 2 and the I over, it's going to be x minus 2 minus I. This one is going to become x minus 2 plus I. These are my 2 complex factors. Now, my 2 real factors, x equals -3 is a factor of x plus 3. X equals 3 is a factor of x minus 3. I would strongly recommend, as you work backwards to try to get the equation that does this, to multiply the 2 complex factors together and then to multiply the 2 real factors together. So when I multiplied the 2 complex factors together, what I did here is I just said, well, I know that this x is going to distribute through every term in this group. When it does, I get x squared minus 2x plus xi. Then -2 distributes through that second group. That's where I get minus 2x plus 4 minus 2i. Then the negative I distributes through that last group. And when I do that, I'll get minus xi plus 2i and minus I squared. Okay, so that's my term for now. These last ones, you know, oh, you're multiplying x plus 3 times x minus 3. That's just going to multiply the middle terms cancel, and I'll get x squared minus 9. It'd be x squared minus 3x plus 3x minus 9. So it just simplifies to that. Now, this first term also has a lot of terms that cancel out. Please notice there's only one x squared term, so I bring it down. I have minus 2x and then minus another 2x for minus 4x. Please notice the xi and the minus xi cancel, the minus 2i and the plus 2i cancel. And so then the only thing I'm left with is this 5. Where did that come from? The 4 minus I squared. Please remember, I squared is defined to be negative 1. So if you're subtracting a negative 1, you're adding 1. So this is the same thing as 4 plus 1. That's where that 5 came from. So now I have both of my factors simplified out, and there I'm ready to go ahead and multiply one more time. So this time what I'm doing is I think I distributed the, the x squared times both of these terms. I got x to the 4th minus 9x squared, then distribute the minus 4x cubed plus 36x, and then distribute the 5x squared minus 45. So I get my polynomial. This polynomial could be multiplying some constant coefficient c. Still need to solve for c. So then f of x is equal to c times this function right here. Now, in order to determine what c is, all I have to do is say, well, I know that f of 0 is supposed to be 90. So what happens if you try to plug a 0 into this polynomial? Every single one of those terms of x cancel out, and you would just have, well, f of 0 is going to give me c times a negative 45. It's supposed to equal positive 90. I would get negative 45 times c is 90. That's going to give me c is equal to 90 divided by negative 45. I know that's going to be c equals negative 2. Therefore, my final answer for this glorious function that satisfies every single one of these criteria is f of x is equal to negative 2 times the group x to the 4th minus 4x cubed minus 4x squared plus 36x minus 45. You can leave the negative 2 factored out front. You could also distribute it in there if you preferred. Either way, it's fine with me. Now, let's go ahead and take a look at our problems where we're looking at rational functions. For number 9, I give you the rational function x squared plus x minus 2 divided by x plus 1, x minus 7. I ask you to list all asymptotes. So that's vertical asymptotes and horizontal asymptotes. Now, even though that this denominator is factored, you can tell that the leading term of that denominator would be a 1x squared. The reason I mentioned that is because the horizontal asymptotes, you say anytime the degree of the numerator and denominator is the same, they are both 1x squared, then the horizontal asymptote is going to be at y is equal to the fraction of the leading coefficients. And again, your term in the denominator would be x squared. If you multiplied it out, it'd be x squared minus 6x minus 7. But it's x squared over x squared. For the leading terms, I just take the fraction of those leading coefficients. I know that this is going to have a horizontal asymptote of 1. Now, the vertical asymptote, even easier since it's factored. You just say a vertical asymptote is anything that's going to cause that denominator to equal 0. You can say, well, it's going to equal 0 when x plus 1 is 0. That's at x equals negative 1. And when x minus 7 is equal to 0, that's going to be at x equals 7. Now, please don't just put vertical asymptotes, and I've seen students do negative 1 comma 7. I would count that wrong. It has to be x equals, because remember, this is literally Yes, it's the location of x, but it's also the equation of the vertical line that you're drawing in there. So I have to see vertical asymptotes, x equals -1, x equals 7. I have to see for the horizontal asymptote, not just a 1, but the equation y equals 1. That is the equation of that horizontal line there. Now, once I have my vertical and horizontal asymptotes, it's best just to go ahead and graph those in. The horizontal asymptote at y equals 1, vertical asymptotes at +7 and at -1 here. Now, I also ask you to state the domain of the function. You can say, well, the domain is easy because it's just broken up by your vertical asymptotes. You would say it's going to move forever to the left and go up till x equals -1. It cannot equal that value, but then it can take on any x value between -1 and 7. So I'd say in interval notation, x is equal to -∞ to -1 union any number between -1 and 7, union any number between 7 and infinity. This is basically all real values of x except -1 and 7, but I will require the interval notation there for that part of the domain. Now, x-intercepts and y-intercepts. You say, well, the x-intercepts, it's just when your function is equal to 0. The only way a fraction can ever equal 0 is if the numerator of the fraction is equal to 0. So you'll see I say set your function equal to 0. That happens when the numerator is 0. If you factor your numerator, it factors pretty easily as well. It's just factors of -2 that sum to get to +1. So I said x plus 2 and x minus 1. So then the values of x that are going to cause that to equal 0 would be x equals -2 and x equals 1. This is where it's going to cross the x-axis. My y-intercept, you just plug a 0 in for x. And if you do that, please notice in the numerator, if you plug a 0 in for x, you'll get a -2. Your denominator, you would get 1 times -7. So it's going to be a -2 over a -7, which is +2/7. I can say, well, my y-intercept occurs at 2/7. Now, from that, you can go ahead and graph in your function. So here's what I did. Knowing that your first x-intercept is at -2, well, that puts me to the left of this asymptote. X equals -2. What do I know the function looks like? Well, as it approaches -infinity, by definition, it has to go up and approach that horizontal asymptote. As it approaches -1, it has to go either up to +infinity or down to -infinity. I know it can't go up to +infinity because you've got your horizontal asymptote here. It's going to go down to -infinity. So use your asymptotes to help guide the graph. Now, on opposite sides of asymptotes, you're always going to have opposite behavior. If one side's going down, the other side is going to go up, unless the factor that caused the asymptote is to an even power. That's not going to be the case on the test. So I can say, well, the factor that caused this asymptote was right here. It's of odd degree. So if it's going down on one side, it's going to be going up on the other. So I can say, well, okay, it's starting upward towards +infinity. It's going to come down in this region. I know it has a y-intercept at 2/7. So the ordered pair 0, 2/7 here. Has another x-intercept at x equals 1. So can you cross a horizontal asymptote? Over here, I was acting like you couldn't cross it. You can't unless you're in between two vertical asymptotes. That's the only time you're going to cross one of these horizontal asymptotes with an algebraic function, is if it's in between two vertical asymptotes. If you're not in between two vertical asymptotes, it will not, and I repeat, will not cross the asymptote. So I can say, or the horizontal asymptote. So this horizontal asymptote, I couldn't cross it, so it made it easy to graph in. Now I knew this side started up, and it's going to come down throughout this region, cross the x-axis at 1, 0, and then keep on going down. Now, it can cross that horizontal asymptote once. It's not going to go back up, though. So it came on down through here. Now, I already know, because I have an asymptote at 7, whatever direction I'm going in one, it's going to be the opposite direction in the other side of the asymptote, because this is an odd degree factor. So I can say, well, then it's going to be starting high and then using my asymptotes to help guide my graph. I know it's going to come down and approach this horizontal asymptote as x gets large, and we would have in our function. Now, whenever you're doing these, I didn't plot out a whole lot of points. If you want to plot out points to make sure that you're doing it right, like you might have plotted out what's the y value when x is 6, what's the y value at x equals 8, to see the points on the graph, you're welcome to do that. It shouldn't be necessary, so I didn't do it, but you're absolutely welcome to if it makes you feel more comfortable. Now, I'm going to go ahead and pause here and do the rest of the problems with a second video, just so this video doesn't get too long and my Zoom doesn't cut me off.